Now we're going to talk about the constant acceleration when there's a special case when motion itself is influenced by constant acceleration all the time. Okay? One example of constant acceleration motion is when we throw something either vertically upwards or downwards or even horizontally. Whenever we have something that is being thrown, we have this constant acceleration caused by the gravity, which will make all objects accelerate towards the center of the Earth at 9.8 meters per second squared. Okay? And that's a safe assumption to have because most of our physics is going to be done near the surface of the Earth. Okay? So we make the assumption that acceleration does not change when it's constant acceleration. Okay? Near the surface of the Earth, where most of us spend most of our lives, right, or times, in the acceleration due to gravity is approximately constant value of 9.8 meters per second squared. Okay? So that value will not change. Okay? That value will not change. And well, even if you're like, if you ask me, like, well, Mr. Kim, what if you like go way up on top of the Mount Everest? Doesn't really change that much, believe it or not. Okay, um, to a point, like it's going to make a huge difference. It still rounds to about 9.8 meters per second squared. Okay, even if it's like the Death Valley, okay, which is like the lowest, it's like lower than I guess sea level, doesn't really differentiate too much from the top of like Mount Everest. All right. So how can we utilize that? Well, here we go. We can use that information by saying if we were to take a look at acceleration versus time graph, when we look at the acceleration versus time graph, and if we are moving at a constant acceleration, that means this acceleration can be graphed at a constant value like this, which is straight horizontal line, right? If you were to think about the area of acceleration versus time, right? The area that represents under the acceleration versus time graph, right? So area which is acceleration times time, okay? If we were to look at their units, acceleration represents meters per second squared times time, which is seconds, we get second cancels out and this square cancels out, we get meters per second. Therefore, that area of base times height represents delta V. Represents the change in velocity. Okay? So, if we were to say, okay, let's just put this down. If, and only if, IFF, that's what it means. It means if and only if, right? T initial is 0, right? Then delta T is equal to T final, which is just T. Okay, so this is only true when t initial is 0. So for that case, right, this t, of course, is delta t, okay? So our acceleration is equal to, right, delta v over t. And since delta v is vf minus vi, okay, divide that by t, and we get acceleration. So if I were to rearrange this equation by multiplying both sides by time, so my vf minus vi then is equal to a times t, which is exactly what we talked about, which is the area of the acceleration versus time graph. And if I add vi to both sides, vi here and vi here, right, then my vf is equal to vi plus at. This is my equation number 1. Okay? Now let's take a look at the velocity versus time graph. If my acceleration is constant, then the velocity versus time graph will have a velocity graph that has a constant slope, because the slope of this represents the acceleration. To find the area of this under the graph, right? To find the area, we have to add this area plus this area. However, if we were to use, what is that, trapezoidal rule or something, right? If we were to use find this area here and place it here, aren't they the same? So I can actually find the area of this rectangle. And that area of a rectangle is same as the area of this trapezoid. Okay? So to find this rectangle, this velocity value is the average of these two velocities. So this should have value of Vf plus Vi over 2. That is this value right here. And of course, this right here is my delta t. And of course, if my t initial is 0, then my delta t is just t. Okay? Therefore, the area, which represents the delta x, right? Area is equal to delta x, right? So we know that this whole area here is equal to delta x, and that is equal to base, which is delta t, times the height, which is this. So Vf plus Vi over 2 times t. This is my equation number 4. Then you're going to ask me, whoa, Mr. Kim, what about equation 2 and 3? You just went from 1 to 4 straight through. Well, if I were to substitute, let's plug in equation number 1 into equation number 4. So I will place this VF into here. Okay? So my delta X is equal to VF, which is simply VI plus AT, right? That's what my VF is, plus VI. And this VI and this VI are the same VIs. Whole thing divided by 2 times time. Okay? So if I consolidate this, my delta X is equal to this VI plus this VI is 2VI plus AT, whole thing divided by 2 times time. I'm going to distribute the time through. So my delta X is equal to 2VIT plus AT squared, right, over 2 over 2. I could split this, right, like that. Therefore, my delta X is equal to 2 over 2 is 1. So I could say VIT plus 1/2. This is what that 2 means. AT squared. This is my equation number 2. Okay? And if I split the delta X into X final minus the X initial is equal to VIT plus 1/2 AT squared, then I can bring this negative VI to the other side of the equal sign and it becomes positive VI. And this can also be representing my equation number 2 as well. They're same things. Okay? Therefore, so now I have equation 1, 4, and 2. Well, let's solve for the third equation. Okay, let's solve for the third equation. So let's write down equation 1. Equation number 1 was VF is equal to VI plus AT. And then my equation number 4, right? My equation number 4 was delta X is equal to VF plus VI, this is the average velocity, divided by 2, right, times time. Let's solve, right, let's solve for time t, okay, and plug it into right, equation number 4. So when I solve for time from equation number 1 and then plug it into equation number 4, let's solve for time. So my VF is equal to VI plus AT. If I bring this to the other side, what do I get? I get my VF minus VI is equal to AT. So my time T is equal to VF minus VI over A. So I will plug this into my time here. Then I get my delta X is equal to, right, VF plus VI over 2 times, right, VF minus VI over A. I can multiply these through and bring it out, right? So I can say delta X is equal to 1 over 2A times VF plus VI times VF minus VI. If I multiply both sides by 2A, I get 2A delta X is equal to VF plus VI times VF minus VI. Curses, foiled again, right? So 2A delta X is equal to VF times VF is VF squared. VF times negative VI is negative VF VI. VI times VF is positive VF VI. VI times negative VI is negative VI squared. So you can see that these two added together will cancel out to 0. So what I have is 2A delta X is equal to VF squared minus VI squared. If I bring this negative VI squared to the other side by adding it, then I get my VF squared is equal to VI squared plus 2A delta X. This is my equation number 3. Now you don't have to know how to derive all this. The good thing is, now that I derived it with you, you can use this at your leisure. Okay? Matter of fact, I recommend that you actually write this out, these 4 equations out, okay, on a small piece of paper, and then tape it onto the back of your calculator so you can have it with you all the time, including during the test. Okay? So let's consolidate everything we just talked about. Here's my equation number 1. My equation number 1 states VF is equal to VI plus AT. My equation number 2 is delta X is equal to VIT plus 1/2 AT squared. That is the exact same thing as X final is equal to X initial plus VIT plus 1/2 AT squared. They're same things. I just broke the delta X up into X final minus X initial and brought the X initial to the other side. Then my equation number 3 is VF squared is equal to VI squared plus 2a delta x. And my equation number 4 states, right, delta x is equal to the average velocity, which is Vf plus Vi over 2, that's the average velocity, times time t. Okay? So if I look at these 4 equations, right, there are 5 unique variables for each of, well, all 4 equations combined. However, in each of the equations, there are only 4 variables. Okay, there are only 4 variables. Oh, look at that. Oh, my hand's a mess. Anyway, sorry about that. Right? There are 5 variables. Namely, VF, VI, A, T, and delta X. These 5 variables, out of the 5, only 4 variables are used in each of these equations. For equation 1, delta X is missing. For equation 2, VF is missing. Equation 3, time is missing. So if you don't have time and you need to calculate something, you use equation number 3. That doesn't mean you use this equation when you're running out of time at the end of the test, okay? This time factor itself has to be missing. For equation 4, acceleration is missing. So when you are reading a problem, write down all these 5 variables. And out of those 5 variables, one would not even be mentioned. Then other 4 variables are going to be, out of those 4, 3 will be known, and you're going to have to solve for the 4th one that you don't know. So the best thing to do is write down these 5 variables, write down all the givens for these 5, and one of them will not be given at all, or not even mentioned, and one will be the one with question mark, and the other ones are the ones, or other 3 will be given values. Okay? That's when you use the proper equation for that. Okay? Now, these are obviously all in the x direction. There can also be equations in the y direction. Okay? In the y direction, nothing really changes, really, right? Except instead of equation 1 being VF is equal to VI plus AT, you'll get VFY is equal to VIY plus GT. Now, G obviously is acceleration due to gravity. Okay? Similarly, right, your delta Y is equal to VIYT plus 1/2 GT squared instead of AT squared. Or simply, you can say Y final is equal to Y initial plus VIYT plus 1/2 GT squared. Then your third equation becomes VFY squared is equal to VIY squared plus 2G delta Y. And lastly, delta Y is equal to, right, VFY plus VIY over 2 times T. So this is where G is equal to negative 9.8 meters per second squared, okay? on Earth. On other planets or moon, or it will have different value. Okay, like on the moon, it'll be like negative 1.7. On Mars, it's like negative 3.8. Right? So it's going to be different G depending on which planet you're going to be working on. Okay, so if you know this, this is easy. Right? So you don't have to memorize both of them. I mean, if you know this, you could derive this. All right. All right. Any questions? Okay. So when we look at vertical motion, right, this way, up and down, okay, we call that free fall motion, right, when things are falling freely, vertical. So when we take a look at free fall acceleration, the acceleration due to gravity will always be, right, negative 9.8 meters per second squared, and that negative represents downward direction, okay? And the, I guess, imperial British system will be 32 feet per second squared, okay? We lost $1 billion worth of satellite because the United States used this and the rest of the other countries used this, and things did not go well, and we lost it. We lost a lot of things that way. Space probes, satellites, sad. Anyway, it's a good idea to get some things standardized, I think. For example, we're going to consider up direction positive and down direction to be negative. We have to standardize that. Okay. We should also say that right is positive and left is negative. And that's the convention that we're going to pretty much use from now on. Okay. All right. Now consider a ball that is thrown straight up. So if you start here and then you throw this ball straight up, okay? You throw this ball straight up. With the initial velocity. What's going to happen? Well, as the ball goes higher and higher, what's going to happen is this ball is going to lose speed. It's going to slow down. Okay? It's going to go up. And as it gets higher, it's going to slow down. Okay? Oops, it should slow down. And then it should stop at maximum height, and then it's going to come back down again. Okay? And as it comes down, it's going to be basically, right? It's going to stop instantaneously at the top. And it's going to come down, and it's going to speed up as it comes down, huh? All right? This is same ball, right? Same ball. So if I were to plot this motion on y position versus the time, okay? At maximum height, at maximum height, at maximum height, your v final at y max. Now, final can be anywhere you want. You can make this your final. You can make here your final. You can make here your final. You can make here final, here final, here final, right? So depending on where you want your stopwatch to stop, that can be your final time, right? Your initial is here, but you could also say your initial here too, and then final here. So you could choose your initial and final anywhere you want. Okay. So in our case, we're going to call that final position at final position at y max, or simply just v at y max is always going to be 0 for the y velocity. So as it goes up, slows down, and stops instantaneously at maximum height before it changes directions and speeds up going down. Okay? But your a sub y, which is g, will still be negative 9.8 meters per second squared. Just because, it stops instantaneously does not mean your gravity doesn't exist anymore, right? Just because I throw something up in the air, God is not going to watch me throw something. He's like, Mr. Kim throws it, stop the gravity, right there, and then, turn it back on, turn it back. No, it doesn't happen that way. The gravity will always be turned on, whether I throw it up, throw it down, or not throw it at all, okay? So here, as it rises, it's going to actually slow down to a stop. So notice my slope at the maximum height should be horizontal, which is 0, okay? And it's going to actually speed up on the way down, just like the way I threw it up, okay? So this should be pretty symmetrical, like that, and come down pretty much symmetrical as well, okay? So this right here is maximum height. And at maximum height, my velocity instantaneously is 0. That means my velocity value should be 0 right here. And the initial velocity is a slope right here at this point, tangent. That slope is my v initial up there, and it's positive, because notice my slope is positive, and I'm throwing it up, so it should be positive. And as it comes down, my slope here is negative, so it should start from the positive velocity. It will go through 0 at halfway point at maximum height, and it should come back down with the negative velocity reaching, right? So here is my V final, right? That's my V final. The magnitude of this should be same as the magnitude of that, except this says negative, this is positive. Okay? All right. So let's take a look at final notes on chapter 2. Remember, when going between the following graphs, right? So when we go from position to velocity, we found slope. From velocity to acceleration, we found slope. And then from acceleration to velocity, we found area. From velocity to position, area. Okay? Derivative, integral. Okay? All right. So here's some hints that you should know. Problem solving with constant acceleration equations. Right? First step is write down all 4 equations in the margin. Well, you should have it with you. I mean, I told you to cheat. Make a little cheat sheet, like small cheat sheet, with all the 4 equations written down. Cut it out and paste it or tape it onto the back of your calculator so you could have it with you all the time. Right? The acceleration due to gravity is a sub y, right? And that's g. And g is a sub y, which is negative 9.8 meters per second squared for free fall problems. Okay? Very important. Sometimes they don't even mention this. So this should be just a given. Okay? 3. Analyze the problem in terms of initial and final sections. Like I said, you could consider any position that you want to start to be the initial at your convenience, and any place final to your convenience. Okay? So you can make your initial wherever you want, final wherever you want. But make it easy so that it's a lot easier to calculate depending on where you put your initial and where you put your final. Okay? Number four. At maximum height, right? Your V at Y max is 0. But your AY, which is G, is equal to negative 9.8 meters per second squared. Five. When object is, let's say, released or dropped, right, from a stationary position, okay, then V initial in the Y direction is 0. That's really good to know. When things are dropped, released, or falls, okay, falls, okay, falls off, the same thing as like sort of released, okay. 6. When an object is thrown upwards, okay, then your initial velocity in y is positive, okay. 7. When an object is thrown downwards, then VIY is negative. Okay? And when things hit the ground, right, usually you talk about right before it hits the ground, right? So technically the object is still moving because it's not hitting the ground yet. So don't think your final velocity is 0 when it hits the ground, right? It's usually right before it hits the ground when we're looking for speed or time or etc. Okay? So especially when it's hitting right before it hits the ground, don't say 0. It's actually not 0. It is actually still moving. Alrighty. So here's an example problem. Okay. A sports car, okay, starts from rest. Look at that. From rest to 95 kilometers per hour in 6.2 seconds. This is my initial velocity. This is my final velocity, and this is my time t. So since it starts from rest, my initial velocity is 0, right? So let's write down everything we know. Vi is 0. My Vf is equal to 95 kilometers per hour, and my time is equal to 6.2 seconds, and they want us to find acceleration. I have no idea about the delta x, right? There's nothing mentioned about delta x whatsoever, okay? So which equation shall we use from this? Come on, somebody shout it out. Yeah, Andy.
Number 1.
Yes, I would use equation number 1, right? However, look at this. This looks like trouble because my VF, which is 95 kilometers per hour, cannot be used because I want it in meters per second. So it might be a good idea to convert that, right? So 1,000 meters is 1 kilometers, and 1 hour is 3,600 seconds. So we should convert that VF into meters per second. And if you do this, I think you get 26.4 meters per second. So this is what we have. All right. So equation number 1 states VF is equal to VI plus AT. My VF is 26.4 is equal to VI 0, right? Plus A times 6.2 seconds. So if you solve for it, my A is equal to 26.4 minus 0 over 6.2, which should come out to 4.3 meters per second squared. Boom. All right. So I would like you to do this for homework, this for homework, and this for homework, up to and including page 37. All right. Thank you for joining me today. I'll see you guys virtually on Wednesday. All right? All right. Have a nice day.
Thank you.
All right. See you guys.
Mr. Kim,
Yeah.
I have a doctor's appointment on Wednesday, so I won't be able to be in class.
When? Wednesday?
On Wednesday.
Okay. Just print out the print out the quiz and then just do it. Work it on your own time. Then would that be okay?
Okay.
All right, Emily. Good luck. Okay.
Thank you.
All right.